We've talked a bit about chirality and we've learned about chirality, but now we need to learn a bit about naming chiral compounds. When we're talking about chiral compounds, like this one right here, what would we name this? Well, you'd be tempted to name this compound 2-bromobutane, right? Because it is a butane, 4 carbons, and the bromine's attached to the second position, so 2-bromobutane. That sounds like a great name to us. Well, that's a pretty good name up until this point, but now that we've gotten to this point in chemistry, in organic chemistry, we've learned that actually this could be drawn as 2 different molecules. This could be a molecule that looks like this. Or this could be a molecule that looks like this. So which one is it? Well, 2-bromobutane could refer to either of these actually. And we've learned that these actually have very different activities in biological systems, or any place where they can bind with something with their shape, right? If they're binding with a protein or anything like that. These have very different results. So we want to differentiate between these two. Well, the way we're going to do this is using our naming again. And the naming that we're going to use a technique that we're going to borrow from our cis and trans. So you remember as we named cis and trans, we actually went into E and Z nomenclature, and we said the way to name something was to assign priority. And if the higher priority was on the same side, Z, same side, remember I said, it's then Z. Whereas if they're on opposite sides, it's E. Well, we're going to borrow that same idea of priority. And we're going to use that priority to help us name these chiral compounds. So let's give it a shot real quick. Well, if we look at this top one right here, what is the priority? Well, number 1 priority, highest molecular mass, is bromine, of course. Number 2 is going to be the ethane, because sure, both of these have a carbon, right? This 3 and 2 here, both have a carbon immediately attached. But we go to the next atom to break the tie, and we notice over here it's a hydrogen, right? Whereas this one is a carbon. So for that reason, the tie winner is going to be the ethane. And then we notice the 4th one isn't drawn, it's our hydrogen. And our hydrogen is going into the screen, right, away from us right here. Now, our rules say this. First of all, step 1 is assign priority. Okay, so that's going to be step 1. Step 2 is going to be make sure the hydrogen is back or going away from us into the screen or into the board, right? So in this case, our hydrogen is going into the screen. By the way, I should say that this is actually the lowest. Make sure whatever is lowest priority is going away from us. But if there's ever a hydrogen involved, that is the hydrogen. All right? So good, we have our hydrogen going away from us. And then our 3rd step is to draw a circle. So 1, 2, 3, like this. And if the circle rotates to the right or clockwise, it's R. And if the circle rotates to the left or counterclockwise, it's going to be S. So how would we now name this molecule right here? Well, this one is going to be, let me give us a little more space here. Okay, how do we name this molecule? This one is going to be going 1, 2, 3 around that way, so that is going to be R, right? So this is going to be R2 bromobutane. All right? So how would we name this other one now? Well, this other one, if we draw in, let's do our priority, let's do our order, right? Our priority is 1, 2, 3, and then where's our hydrogen? Our hydrogen is right here, coming out at us. 4 is going to be hydrogen. Now there's a problem right away. We notice step 2 says make sure the hydrogen is in the back. Well, it's not, right? So what we're going to have to do is we're going to have to rotate this entire molecule around. Imagine me just grabbing the left-hand side right here. Imagine me just grabbing onto this left-hand side and spinning this whole thing around, right? So what would happen if I spun this whole thing around? Well, we now have this shape right here, right? And our Br is now coming out at us, right? Going into the screen away from us is the hydrogen now. So let's go ahead and take a look. What would these priorities be now that we've flipped it? Same priorities, right? 1, 2, 3. But notice we've spun the whole thing around. By the way, if it's difficult for you to mentally spin the molecule, you could also think yourself about spinning yourself, going around. Imagine yourself walking around this molecule and looking at it from the back, right? So we were looking at this molecule from the front, and we had to walk around and look at it from the back so that that hydrogen would be going away from us, all right? Now that that's going away from us, we have 4 here, right? So we now have 1, 2, 3 in this direction. So what is this? This is S, right? It's counterclockwise. So how would we name this? How would we name this molecule? This would be exact same as before, right? We're going to have the same name with one important difference. This is now an S2 bromobutane. Now, the fact that these are exactly the same, but they are R and S, means they are mirror images of each other, as we expected when we first drew the two options. So these are what we call enantiomers, right? These are enantiomers. So I want to talk a little bit more about how these enantiomers would look if we drew them out using, let's say, a Fisher projection. What would that look like? Let's say that we were looking at this molecule and we wanted to do a Fisher projection. Well, the way I'd recommend doing that is also imagine this hydrogen back here, right? It's going away from us. And then imagine that you are looking at it from this angle. Now, why would we want to look at it from that angle? Well, Fisher projections are defined in this way, as we've talked about. Fisher projections are defined I like to draw them like this the first time I draw a Fisher projection. The two things coming at us are horizontal, and the two things going away from us are vertical. So this is just the way we represent them on flat space. But to save time, we just draw it like this, right? But there's always a carbon at the center here, and always up and down is going away from us, and horizontal is coming out at us, right? So let's go ahead and take a look at what this would look like with that eyeball. Well, if I imagined that I put this ethyl here down, so imagine I'm almost looking at it from this perspective, right? So the ethyl is down and I'm looking at it this way. So what's that going to look like? Well, if you imagine it from that perspective, then the Br would be here on the left, right? The H would be here on the right. And here we have our ethyl, essentially. Just going to draw it like that. And on top, we just have our CH3. Okay? Probably more often you'd see this written as CH2, CH3 like this, little condensed formula there. But this is the way to represent our chiral molecule. If we use the Fischer projection in this way, it can be really nice because what we can do is show the enantiomer simply draw the enantiomer by drawing CH3 again on top, right? CH2, CH3. And we can take the mirror image. Now the mirror image is going to have a hydrogen here, of course, and a Br here. So those two are mirror images. So these are enantiomers of one another. All right? Now, let's look at a little more complicated Fischer projection to see what else can happen. What if we were to have two chiral centers? So what if, and I'm going to use a Fischer projection here because it makes it a lot easier to draw these. Now, let's just say that these, of course, end in CH3. All right? But we're going to put some interesting things here. So let's start by putting two hydrogens. And then let's put a chlorine and an alcohol. So this now, as you notice, has four things that are different attached at both of these centers. So if I was to label my chiral centers now, I have two chiral centers. So what would happen if I, let's say, take this molecule and kind of let's make some changes here. So let's say that I was to put the other alcohol here, the Cl here on the left, and then on the right, I would put both of these hydrogens. All right? So this is what we would call an enantiomer, right? Now, we looked at enantiomers with one chiral center, but here I'm telling you, if you have two chiral centers and everything in the molecule is still a perfect mirror image, that is still the whole molecule is still a mirror image. So it is called an enantiomer. So if we were to compare these two right here, we would say that these are enantiomers, right? Now, what if we were to try something else? Let's try just switching one of these. So let's put the OH over here and the H back over here. So what would this be comparatively? Well, we're actually going to call this a diastereomer. Okay? This is a diastereomer with both this one and this one. What that means is it actually is exactly the same, right? These two chiral centers are the same, but these two chiral centers are different. So it's not a mirror image. It's the same at one, but different at another. And then if we do the same comparison, let's say at the top, what we notice is this chiral center is different than that one, but these are the same. So those are diastereomers. Now, if we've noticed, we've drawn the molecule all the ways we can, except for one. We can still do one more thing, and that would be to make a mirror image of this one. So let's briefly try that out. So what could we do here? Right, let's put our mirror image in. So we would have an alcohol here, and we'd have an H here, and then we'd have over on this side an H and a Cl. So that would be, of course, again, that would make these two enantiomers of each other. And it turns out that that one we just drew would be a diastereomer of the two on the left, right? So in every single case, if we picked one of these molecules and asked what would its diastereomer, it would have an enantiomer, right? That's its pair. So these, of course, should probably do that in this color. On either side, these are enantiomers and enantiomers, right? But if I picked any of these molecules, let's say this one I've circled, its diastereomers are these two, right? What if I was to pick this molecule? What would its diastereomers be? It would be both of these enantiomers on the other side. So these are the different ways to arrange two stereocenters. You notice with two stereocenters, we now have 4 molecular options, and we have diastereomers and enantiomers that are possible. As we expand past 2 chiral centers, it becomes exponentially more complex. But remember, an enantiomer is where every chiral center is mirror imaged, and a diastereomer is a situation where we have some matching and some not matching. All right. So let's look at one more example of something that can happen. It's a little interesting. So let's say we have another molecule, and in this time it's just a 2,3 bromobutane. So what would happen? How many chiral centers do we have? I'll give you a second. Think about how many chiral centers we would have. That's right. If you said we would have 2 chiral centers, you're exactly right. Here are both of the chiral centers, right? So how many different molecules can we produce from this? How many options do we have? Well, if you paid attention to our last example, your immediate answer is going to be 4. We have 4 different options, right? So let's take a quick look at some of these options. Well, first of all, and I'm going to draw Fisher projections because it's going to make it a little easier for us to see this, okay? So the first thing that we have that we could do is we have a Br and a Br on this side, an H and an H, right? And here we have CH3 and another CH3. Now, what's another option we can do with this? And let's just go ahead and get rid of this so we have some space to talk about this. What is another option we have here? Well, we could put the BRs over here and the H's over here, and we'd get CH3. All right? Now, what is another option? We can move our BR on opposite sides like this. And our final option is that we can mirror that. All right? So those are our 4 options and our 4 molecules. So you might be proud of yourself that yes, you were right. There are 4 different options. But hold on, there's something I need to point out that is very interesting. If you take a close look at this molecule right here, I'm going to redraw that for you, and I'm going to redraw it in 3-dimensional perspective formula. So let's say that that molecule, and I'm going to kind of draw it a certain way on purpose for you. I'm going to draw the center bond straight on. Okay? And then I'm going to draw a CH3 up, and another CH3 up. Okay? Now, why did I do that? Because if we remember, when we're drawing a Fisher projection, everything vertical is away from us. So if I'm looking at this Fisher projection right now, I can almost imagine a person standing right here and looking at this from the Fisher projection side, where these things are going away from us, right? The vertical things are going away from us. So what does that mean would be coming out over here? Coming out of the screen towards us, right? Well, that would be the top one, so that would be this BR. Now, what does that mean would be over here coming out of the screen at us? A BR, and what does that mean? Is right here is an H, and what is right here? An H. Actually, let me draw that a little better so we can see it. I'm going to put that H over here, just so we can see how this lines up a little better. There's something really important for you to notice that some of you might already be noticing. If you imagine a mirror here, what do you notice that mirror would show us? Well, that mirror is showing us that there's actually symmetry in this molecule. Remember, things that are non-superimposable mirror images, they don't work, right? We can't superimpose one on another, right? And left-handedness, right? But that's because they're asymmetric. Notice that there is actually symmetry in this molecule, right? Do you see the symmetry here? And what does that mean? That means that if you spin this thing around, it would actually be the same exact thing as this one here, right? That makes sense? So what I mean by that is, if I were to draw the mirror image of this molecule, let's just do it real quick. Well, let's say that we held this thing up to a mirror and we saw it reflected in a mirror. It means that this over here would be coming out at us, right? I'm sorry, going away from us. This right here would be going away from us. The hydrogens would be coming at us. And the CH3s would be up like this, right? That would be the mirror image. Well, what do you notice about this? Something really interesting. What if I took this molecule, I didn't break any bonds, and I literally just spun it around, like on this axis, I spun this around. Not the mirror image, I just spun it around. Notice it would be the exact same molecule, right? Those BRs would both be coming at us now, and nothing would have changed. So this actually is superimposable. It's very odd, right? We have an asymmetric center here and another one here, right? Don't we have two asymmetric centers? Yeah, we do have two asymmetric centers. But because we have symmetry in this molecule, it's what we call a meso compound. A meso compound has asymmetric centers, but also has a line of symmetry within the molecule. It turns out that if we dissolve these into water, they will not rotate the plane of light. They are not chiral, even though they have chiral centers, because of that plane of symmetry. Now, what about these two over here? These do not have symmetry. If you draw these out or build them and you spin them, you'll notice that they are not superimposable. So these are not meso compounds. So it turns out that you have to have a certain chiral outcome at each of the carbons to get that meso compound. This means that if we draw as many as we can, there are not 4 compounds that we can draw here. There are actually 3 compounds that we can draw in this case, because 2 of them are exactly the same due to the meso compound idea. So hopefully that helps you start to recognize meso compounds. I'll warn you that they can sneak in here and there in organic chemistry, so you want to try to be familiar with them and be always looking for that molecular symmetry, even if there's asymmetric centers.